Okay, hello. Thanks for coming along to today's session. I hope you're all keeping well in these current times. I'm going to talk a little bit about evolutionary architecture this evening. Here's some of the things we'll try and cover today. I'll explain a little bit about what evolutionary architecture is. We'll break down the key components and try and go through each one. And then we'll talk a bit about how you might start to build your own one. So a quick bit about myself. I spent about 10 years working as a software consultant, working with lots of different teams and domains and tech stacks along the way. About a year ago, I then joined Codurance as a principal software craftsman. A quick piece about Codurance. We are a software consultancy with the values of XP and craftsmanship at our core. And our mission really is to sort of promote good practices and quality standards within the software industry. So Codurance was essentially born out of the London software craftsmanship community, where a bunch of like-minded people who were passionate about building software and building it in the right way, and generally trying to raise standards of software in the community. And we help companies establish and evolve their software development capacity, aligned with business objectives. We offer a range of different services to cater for different needs of our clients. There's some of them on screen at the moment that you can see. So let's jump into it. What is architecture? In truth, there's no real sort of standard term used in our industry for defining what it actually is and what it means to be that. So instead, let's look at a few quotes from various people that have tried to talk about architecture in the past few years. So the first person is Martin Fowler, and he said, software architecture is the decisions which are both important and hard to change. So those were his thoughts. Simon Brown, architecture is about understanding what you need to build, creating a vision for building it, and making the appropriate design decisions. And lastly, Ralph Johnson says, architecture is the decisions that you wish you could get right early on in the project. So there's something here about things being hard to change and decisions, and making the right decision can have a really big impact on the quality of your software and your project that you're building. But let's think about the classic kind of process of how we build architecture for a second. It tends to look a little bit like this. It's generally quite linear in the process. So generally we start off by doing some architecting and designing at the kind of first step, where we generally make the hard decisions up front about how we will build and design our software. And then having done that and kind of mapped out how we want to build something, we then go and do some development. And we sort of pretend that this is the easy bit, right? This is kind of writing code, and codes, that's our piece, and we'll kind of write that, and that'll be lovely and nice and easy. And then releasing, well, that's somebody else's job, right? That's also easy, so that's no problem there. But in truth, we tend to know the least up front when we very first architect something. We actually learn the most during the development phases, where we uncover false assumptions, etc., and things like that, and we learn more about our domain and our context. And in fact, releasing is really difficult, and it is really hard, and people have written books about this and created tooling and design just for that. So evolutionary architecture proposes the following process instead. After we release something, we take some time to reflect on the change that we've made. We release a new change into production, we gather some data, and then we reflect on whether or not that decision that we made were the correct ones to make. In effect, is our architecture still moving in the right direction? But why is that reflection point important for us? Well, if we think about the world today in which our software systems run in, then one thing is quite clear, right? Change is inevitable. Whether we like it or not, our software and our architectures are going to have change thrust upon them. There is changes in technology, such as language choices or libraries or frameworks, and even things like environments where we've cloud and serverless have become quite popular recently. There's also sort of the non-technical changes too. So thinking about different revenue models, for example. So years ago, people were buying physical music, and much more nowadays, it's more moving towards sort of rental, so Spotify and things like that. Changes in competitors, changes in customer needs as well, for example. So users are now demanding more richer user experiences than they were before, and being able to access products on different devices, whether it be tablets, desktop, and mobile phones. So we know that change is coming, whether we like it or not, and it's often very difficult to predict what that change will be and what it will look like and how it will impact us. So evolutionary architecture is all about trying to embrace the fact that we know change will happen, and try to build that concept into our software from the very beginning. So Neil Ford, Becca Parsons, and Pat Qua, my former colleagues, they define evolutionary architecture in the following way. An evolutionary architecture supports incremental, guided change as a first principle along multiple dimensions. So there's quite a lot to kind of unpack there, and thoughts going on in that sort of those three lines. So let's dig into actually what does that actually mean in practice. So the first thing there is this concept of guided change, and what does that actually mean? So it's about setting the direction we want our architecture to go in, and trying to put in mechanisms to keep it on track and notify us when it's moving away from that target. The question is, how do we know if our architecture is good? What does good mean in that context? How do we know if it's degrading or getting worse? Well, we can borrow a concept from evolutionary computation to help us with this, which is called fitness functions. A fitness function represents something you are trying to achieve, essentially. So in the evolutionary computation world, you generally start off by defining a fitness function, and then the evolutionary algorithm will attempt to find a solution to match that fitness function requirements. So in effect, you're defining the parameters for what your solution needs to look like. So the naming may be a bit new to you, perhaps, but I'm quite sure that you've used these things before in your software and in your design. For example, if you've done any form of performance testing, for example, that is in effect a form of fitness function. You would have likely defined a threshold value for where acceptable performance is, and then you would have written some sort of performance test that would have either passed or failed, depending on whether or not it was under or above that threshold. So in effect, you've written a fitness function that you've defined the boundaries of what good means for performance of your system, and that test will either pass or fail, depending on how well the system behaves. Also, there are some quite nice tools out there that enable sort of automating fitness functions. So tools like JDepend, for example, in the Java world, and also ArchUnit, again in the Java world, enable us to put automated tests in place around modularity and dependencies within our code bases. The key thing about fitness functions is that they should be something that people cannot disagree on. It's a little bit like defining what done means for a user story. It should have common agreement across every people in your team, and it should be very clear whether this fitness function is met or not met. Our target architecture then, or what good looks like for our system, is then the sum of all of our different fitness functions combined together. So what that means is we can focus on characteristics and qualities of our architecture rather than implementation details. And we can use those characteristics and how well they're behaving to determine whether or not we're building something that we need to, building it in the correct way, and whether how it's evolving is evolving in the right way. So in effect, these fitness functions act as guardrails for your architecture. They give us feedback on our architecture and let us know when it's moving away from what we defined as good. So there are quite a few different types of fitness functions. Let's quickly sort of go through each one, and I'll give a few examples of each one as we go. So the first one is atomic fitness functions. So you can think of these as they generally exercise one aspect of your architecture in isolation. So an example here might be you have a unit test that will verify some sort of modularity within your code base. So for example, maybe you have an e-commerce system and you want all of your kind of customer related code to live in a customer related package. You can write a unit test that kind of enforces all of the customer related class and behavior lives in that package, and then anything that's added that isn't in that package, the test should fail and tell you that the modularity is kind of being broken in that step. Next one is holistic fitness functions. So these generally exercise multiple fitness functions together. So you might have one, for example, around security and scalability. And quite a good example of this one is the Chaos Monkey from Netflix, for example. So this is a case where we're hammering our system, but we're exercising multiple different fitness functions together and seeing how they interact and how they behave. We have also triggered fitness functions. So these run based on a certain event occurring, whether it be a time-based thing or a manual intervention. So whenever we run a unit test, for example, whenever that is executed, that's also classed as a triggered fitness function. We have continual fitness functions. So these execute a constant verification of our system and of our architecture. So a nice example here is sort of monitoring-driven development. So if you have a system where you're kind of sending in sort of would-be but fake transactions to your system, that gives you the chance to exercise your system in its entirety and see how things behave. I've been on teams that have had these kind of sort of monitoring-driven development situations set up where they're constantly kind of passing through dummy transactions to get a sense of how their system's performing constantly. Next up, we have static fitness functions. These have a fixed result, so they either pass or fail. So, for example, here might be a test to check whether our code base would pass or fail against some predefined threshold of complexity. Then we have dynamic fitness functions. So these rely on a shifting definition based on extra context. So, for example, quite often you'll have to trade off different attributes of your system. So we might say we'll be okay to accept a slight degrade in performance if we're able to scale the overall system in a better way. We also have the kind of automated fitness functions, and generally these would run in kind of a sort of classic CI/CD pipeline. So whether these are things like security checks, we're running testing based on things like Arch unit or simple unit tests, things like those kind of live in our CI/CD pipeline. We also have a certain class of manual fitness functions. So sometimes we have systems that will have requirements placed on them that are quite hard to automate, and so we do need to rely on some kind of manual intervention there. So, for example, there may be a reliance to sort of comply against some legal requirement, for example. So we need to make sure that our system, as it evolves, we don't break that requirement. And then there's also temporal fitness functions. So these tend to be around capturing dates that have importance somewhere in our architecture. And quite a good one here that I've seen in sort of different teams is encryption certificates that expire. I've been in a few teams where there's sort of been a last minute panic because they've realized that their certificates will expire in the next few days, and sort of trying to kind of renew them just in time before everything kind of stops working. So you may have a fitness function that alerts you in good time about the fact that these certificates might be expiring, and so you need to kind of take action to resolve those. There's also domain-specific fitness functions. So these generally would be around industry regulatory requirements. So if you're working in sort of the banking industry, maybe there's something around fraud prevention or detection that you need to kind of be aware of and try to capture that. So we looked at what guided change generally means, and the idea of fitness functions can help us there by plotting out a sort of set of guardrails for our architecture, defining the characteristics that we need our system to perform well against, and having these fitness functions constantly running, enabling us to check whether what we're building is kind of conforming to these requirements. The next thing to look at then is this idea of supporting change across multiple dimensions. What does that actually kind of really mean in practice? So generally speaking, when we're defining what good looks like for our architectures and kind of writing these fitness functions, we're also thinking about a range of different qualities that we want our software to sort of behave against and perform against. And quite often there will be things that are in conflict. The classic one probably is sort of security and performance. These tend to be in conflict quite a lot. And so quite often as architects, one of our biggest concerns and biggest worries is these trade-offs between these qualities and getting the right trade-off for your system. So changing requirements as well as all of the non-functional requirements as well. So from a business perspective, often sort of thrust on our system. So, for example, recently we had the sort of the GDPR requirement sort of thrust upon our systems. So there's often sort of requirements that come to us from a business perspective, besides just sort of those tech requirements. That as an architect, you have to sort of trade off these things together. And all these different things that we have to kind of sort of trade off, these different qualities, is often sort of a bit like spinning a plate for an architect. It's kind of trading off all of these different attributes that we need our software to exhibit. But we can't have the perfect performance across all of them. It's trading off in the right places to get the right performance for our system, given the context that we're working in. And finally, let's talk a bit about incremental change. So we mentioned previously that change is inevitable. Whether we like it or not, our architectures will be subject to some sort of change. And when this change does happen, we don't want to have to make large sweeping changes to our architectures to support these changes. Instead, we want our architectures to allow us to make small incremental changes over time. A bit like sort of driving a car. You want to sort of make small kind of sort of small tweaks to the steering wheel rather than having to sort of make large sweeping sort of changes as you sort of drive down the road. So we talked a little bit about evolution and kind of this evolutionary architecture. I think it's useful to have a think about that in the sense of sort of thinking about evolution sort of, in a biological sense. Evolution happens over generations in biology. So our architectures evolve through releases. In effect, a new release of our software and our architecture is a new generation. What we want to optimize for then, therefore, is the ability to be able to evolve fast, i.e. to deploy new versions of our architecture on a regular basis. To do that, we need to adopt a few engineering practices, which we'll have a look at now. So if we go back to this idea of, again, kind of evolvability and wanting our architecture to be able to evolve quickly to keep pace with the rate of change that's happening around us, we need to ask ourselves really kind of what is our current cycle time. That's important because our cycle time effectively is the time it takes to get a simple change from development all the way to production. So that cycle time is the time it takes us between generations of our architecture. And we want that to be as quick as possible, ideally, but we also want that to be done in a reliable and repeatable way. So that's an important thing to focus on there. The longer our cycle time means the longer the feedback cycle is between making a change to our system and our architecture. And so longer the feedback cycles are means that it's harder for us to sort of get a grasp on whether our system is moving in the right direction and changing in the correct ways. So all of this is kind of essentially the idea of continuous delivery, which is majorly important. We need to know that deployment has been done properly. We need to know that what the environment state looks like at any given time. And we need to have deployments that are repeatable and tests that are automated and can be repeatable. Deployment should be a sort of non-event and dull event. Quite often, I saw teams sort of celebrating deployments. What I'd say is, rather than celebrate deployments, you want to celebrate getting features in the hands of your customers. That's where the real value is. And so to do this, we need to be able to embrace a culture of automation to give us reliable and repeatable process. To automate how we build our software, how we deploy it, how we build our infrastructure, and so on. Once we have all these things automated, we need somewhere to run them. And that's where deployment pipelines sort of generally come in, our sort of CI/CD pipelines. They're generally a really good place for executing our fitness functions we mentioned earlier on. Having our fitness functions kind of running in a CI/CD pipeline, what it means is they can act as quality gates for our system and for our architecture. What this means is that every new deployment that goes through every new change to our software and our architecture goes through these set of quality gates. So anything that would result in a degradation would stop the deployment pipeline. So we're constantly making sure that every new generation and every new release of our architecture has to conform to these kind of predefined fitness functions to check that the behavior of our system matches the predefined fitness functions we defined earlier on. And what all that means is that we can be sure that our CI/CD pipeline effectively acts as kind of a gatekeeper for making sure that our architecture doesn't move in the wrong direction. And if it does, the pipeline is stopped, and we can take action and sort of look into why that's happened. I often see teams that do a great job of this with the software code, but then struggle with the sort of the database side of things. So what I generally say is try to include the database as well as part of your deployment pipeline. To have a truly automated and repeatable application deployment pipeline, you need to have all the changes to your database as part of the same release process. This can be done as part of the application itself. There's also tools that you can use to do that for you. So things like Flyway or Liquibase or many others to manage sort of database schema changes in an automated way, so you can have the same reliable, repeatable process for deploying a database as you can for your software application. So components within our architecture are going to need to communicate with each other. And Postle's law is very important to think about here. So Postle's law is an important practice because it supports that kind of underlying foundational thing for supporting evolvability. The minute you start to send some data out into the wild, whether it be via an API resource or an event message or anything else, other teams will start to expect that data piece to always be there for it to consume. And so, in effect, you've made a contract with the outside world, whether you know it or not. So John Postel is the man behind Postel's law, or what's also known as the robustness principle. And that says you should be conservative in what you send, but be liberal in what you accept in any communication exchange. So, for example, only validate the data that you need and not an entire message, for example. If you have a customer address, for example, and you only really need the name, there's no need to validate the postcode and things like that. If that does change, what it means is that you need to change your system too then. So you're coupling against things that you don't need to be coupled to. You're introducing a change when you don't need to introduce it. Another important consideration along those lines then is kind of appropriate coupling. Obviously, we need some level of coupling between the components in our system to allow them to work together. But too much coupling and things become hard to change. We want to be able to evolve different parts of our architecture individually based on need. So generally, when I think about how I build systems and components, I sort of generally think about building components around capabilities. And then thinking like that, if you think about sort of the end-to-end user journey, what you can do is kind of combine different capabilities together to build out user journeys. So, for example, you might have a recommendation capability, you might have a capability around taking payments, maybe there's one around sort of showing products. All of these all of these things can be stitched together then to kind of form the overall end-to-end user journey, but are in effect themselves distinct business capabilities. It's also worth thinking about different architectural styles also come with different levels of coupling. So it's important to think about for your use case which of these coupling levels you're happiest most with, and also kind of being quite explicit about why you've chosen these particular types of design. So, for example, I've put down 4 here. If you think about going from the top, so monoliths are generally kind of unstructured, so they generally have high coupling between components. Changes in one area of the code base may have an impact on other parts of the code base are entirely unrelated. So we may have kind of a UI change that suddenly affects the database, for example, because there's no structure in how we built the monolith. So the next one down is a modular monolith. Each component is kind of functionally cohesive and generally kind of communicates with each other through well-defined interfaces. So they're still deployed together as a single deployable artifact, but when we're making a change in kind of each of those modules, it's a self-contained change. Microservices, so they're generally kind of independently deployable things, and the coupling generally there is kind of through integrations with other services. So generally with microservices, we're talking about kind of API calls, HTTP and things like that. And then lastly, kind of event-driven. So event-driven architectures, the coupling generally is at the message level. Kind of we're passing our messages, and that's the level of coupling that we have at that point. It's also worth mentioning here a little bit about Conway's law as well. I think it's quite a well-used quote in sort of many presentation slide decks, but I often sort of see people who are aware of it, but sort of also kind of overlook it in their companies. So it is worth just taking the time to sort of think about it here too. So Melvin Conway said that any organization that designs a system, defined more broadly here with just an information system, will inevitably produce a design whose structure is a copy of the organization's communication structure. And generally speaking, what that means is we want to favor cross-functional teams over teams that are based around a certain skill set. So what this means is that if we have teams, for example, based around functional areas such as a database team or a UI team or a back-end team, then the systems that we build will naturally have these hard separations. And what this means is that systems built in this way are typically quite hard to evolve, because to support a business requirement, that will generally mean that we'll have to change lots of different systems to support that one requirement. And what that means is we're then kind of bringing in coupling between different teams and coupling along contracts, coupling along sort of release cadences, and all these things, which are then kind of hard to maintain and hard to change. Instead, we want to build teams around capabilities that consist of a mix of skill sets. This means that each team has all the skills needed to design and build and deploy their software. This allows teams then to as a result, be independent of other teams and own their architecture and evolve it independently too, which is really important. So they become experts in their domain and are best placed to know how to best evolve their architecture. But perhaps a bit more than that, we want teams to own a full capability end to end. This means that they have the full ownership of that product. Think of it in a kind of a product sense. And they're then able to operate independently of other teams in the organization by having that full end-to-end ownership. Quite often in the past, you'd see teams that were sort of front-end and back-end split, where you'd have a team that would own maybe the front-end part and the team owning the back-end part. But any kind of one business change would likely result in a full sort of back-end and front-end teams working together on that. And so you've introduced coupling there between the two teams. The back-end team has to do their change, then the front-end team has to make their change to also kind of make that available on the UI, for example. So being able to release that to the customer means that you have to coordinate and align across two teams and two systems. So generally speaking, where do we start with evolutionary architectures? I think it can be useful to have a think about the systems in our organization across kind of four categories. So generally speaking, you tend to have four different types of system. So the first one is generally systems that are commodity based. So these don't really require much change. They don't really generate much value. So it's things like an email server, for example. It's an important thing, but there's not a whole lot of value there, and we don't really change this sort of system very much. Then we have sort of general support systems. These systems are generally there to help us do some work in supporting us building and writing our software. So these sort of systems are things like Jira, for example, for sort of managing our Kanban board and our tickets. We need to have some level of customization here, but it's not kind of a really key differentiator for us. So there's not too much that we need to sort of support here and change. Then we have these sort of experimental type systems. So maybe perhaps we're making a bet based on an idea that we have about the market we're working in. We might just look to test out an idea that we have with these types of systems. And so whilst their value could be quite high, in fact, we don't really want to change them or need to change them too often, because the idea is that it's a sort of a way to sort of dip our toe into the market with an idea, see if the idea works or not. And if it does, great, we'll take that learning and build something. Or in fact, perhaps it hasn't worked, then we'll throw it away and we'll start again. And then sort of top right-hand side here, we have the strategic systems. And these are the systems that really kind of add value to our organization. And these are the ones that, generally speaking, they need to support the business and changing needs constantly. These are where we're adding real value to our organization, and they kind of make us different in the marketplace. So this is where you want to focus your efforts in kind of applying evolutionary architectures, really. Out of the 4 systems, the other three types of systems don't really lend themselves and aren't really a good fit for kind of trying to implement evolutionary architecture. These sorts of systems are the best place for looking to kind of implement evolutionary architectures around. So finally, I want to sort of touch upon some pitfalls of evolutionary architecture to kind of have a watch out for. There are some things to kind of have a sort of keep an eye on as you're sort of on your journey to building an evolutionary architecture. The first one is the sort of the last 10% trap. So generally speaking, you want to avoid adopting tools that, on the face of it, seem to provide pretty much everything that you need from your perspective. And whilst you might get a short-term gain, therefore, on kind of productivity, eventually that there'll likely be a business requirement that doesn't quite fit the tool that you'll need. And as a result of that, you'll end up spending a large amount of time delivering on just that last 10% of value that you really need. And this happens for a range of reasons. It could be that the models that you have in your team, in your business, they aren't quite the same as the way that the tool has modeled problems and things like that. So the domain models, for example, that you love and you sort of evolve as you go on in your business and in your software, they're likely to be different in those systems. And so keep an eye on kind of what that modeling looks like. If it's too different and sort of moving away from your own models, that could mean that at some point there will be a painful change coming ahead when you do need to add something that the model doesn't quite fit. The other one is kind of coding via config. So configuration gets quite complex quite quickly. Perhaps you're using a UI, for example, to sort of set up configuration parameters for a given tool. Over time, though, you'll want to have the fast feedback mechanism. If you're looking to go down the route of having an evolutionary architecture, and sort of having these nice fitness functions and kind of automation via a CI/CD pipeline, you're baking in this kind of fast feedback mechanism, and so you'll want that here in this space too. You'll want to know that if I apply a config change, has that config change worked? Is it correct? Are there any problems? You'll want that quick feedback. And so as a result of that, we'll have to start treating our config as code. So having it in source control, having it being run through our deployment pipeline, having our fitness functions kind of run against them, releasing it to different environments in an automated way, and all these things that we're doing to or should do to our software, we also want to apply the same thinking and same mindset to how we're applying config. The next kind of try to avoid it is kind of product customization. So generally speaking, buying products off the shelf may be fine for you, if that makes sense for your space and where you're working in. The key thing though is kind of how much customization that you'll need to do on the product to actually fit your needs. If it's too much, then what it might mean is that you're very much tied into the product vendor's backlog and the roadmap for that product. So for example, you might need to have particularly important change to be made to support a really important requirement for your business. But what could happen is that you'll end up being behind other items in that vendor's backlog. So you're competing with lots of other items on that backlog, and maybe even requests from other companies, for example. So if you are doing an evaluation of looking at buying an off-the-shelf tool, it's really important to understand what that roadmap looks like. Is that roadmap going to be in contention with your own roadmap? Is that product going to be changing in a way that goes against kind of how, like, what you need from the product, and sort of get a sense of how much change you'll need to make in that space, and be comfortable about what the change process would need to be. And finally, the last one here is unnecessary coupling. So again, sort of going back to the idea of coupling and different types of coupling in different architectures. Have a think about the different coupling types that exist in your software today, in your architecture, and kind of what level of cohesion you need between components. It might well be that for your needs, a modular monolith is all fine and good. That might be fine. It might be that actually you're in a place where you have a monolith, but you're finding it hard to scale your teams, and so therefore maybe you need to kind of break that into microservices or kind of event-driven type systems, where you have teams that are better to run capabilities to be able to scale your team and scale your business software development effectively. So have a think about that. That's also an important piece. So I guess some sort of further reading around this, if you're curious. There are some really good books in this space. Obviously, the main one probably is Building Evolutionary Architectures by Neil Ford, Rebecca Post, and Pacwa. But I think the underlying one is probably still the Jez Humble, Dave Farley book around sort of CD and CI. There's some really good things in there, and sort of really good underlying practices to kind of think about, and kind of automating CI/CD pipelines, and kind of getting that as a first-class thing in your system. So that's what I have for today. If you want to read more, those books there are really good resources. But I think there's probably a little bit of time for some Q&A. So if there are any questions, I'm happy to answer them.
Thank you.
Thanks.
So we will give it another moment for some questions to roll in. So it does look like we have a question. The question is, an architecture decision which needs to be made in the beginning of a completely new system is if you create your own framework or pay and use an already created framework to handle authentication, DTOs, and general system piping. What is your advice and experience on what frameworks to use?
Okay. So I think what I would generally say is I'd kind of go back to the idea of the 4 quadrants from my earlier slide, and think about the things that you're trying to build that add value to you and your customers. So, for example, things like authentication, that's generally a pretty well solved problem, and there are people that are very good at that and have built some great frameworks for that already in the industry. So I probably would advise against building your own framework for handling authentication, for example, because that's a pretty well solved problem, and that in itself doesn't add value to your bits and your software. So generally speaking, I think like if there's things out there that are what I would class kind of commodity, so things like authentication, logging, monitoring, like there are already quite good tools and frameworks out there for that already. And so I'd be very surprised should you have to kind of build your own for those. Instead, you want to focus on building the parts of your architecture that are value adding. So the bits that kind of differentiate you from the other people in the marketplace.
Thank you. We have a couple more questions for you. The next one is there any open source code or pipelines that we can use to take a look at an evolutionary architecture in practice?
That's a really great question. I'm trying to think of a good example. I can't think of an open source example that I can share at the moment. But I think if you look at some of the tooling around like some of the Netflix work, for example, the way that's been built. So things like the Chaos Monkey and some of those things like that's generally quite a good example of kind of evolutionary architecture, because it's sort of changed as differing needs have been forced upon it. But I can have a think about that and kind of perhaps share that afterwards if I think of some more. But generally speaking, I think if you're looking for examples of good evolutionary architecture, I think instead I would probably have a think about the principles first, and then sort of go and have a look at where you've seen those principles kind of work well.
All right, thank you. Our next question is, do you have any examples of where evolutionary architecture has worked or not worked?
I do. I don't know how well I can share them though. But I mean, I've worked on a number of different clients that have managed to adopt and process of kind of evolutionary architecture well. So, for example, like I worked on a retail client in Europe a few years ago that effectively kind of replatformed their quite large modular, that's a large monolith website, and broke that down into a set of quite discrete components. Again, like along the lines of what I was saying before about building teams around capabilities. So they had like a product team, for example. They had a warehousing team, a catalog team, I think, a recommendations team, and each of those teams owned the full slice. So they kind of had a micro front end kind of approach where every team owned their individual part of the UI, and then at kind of browser rendering time, it would kind of feed in all of these different parts of the UI to build the final UI that the user saw. So things like sort of the top and bottom navigation, like the searching, recommendations, they were all built by different teams. Like, but from the UI's perspective, it all looked and it felt like it was the same UI. So that was what I meant was that the teams could evolve and deploy independently and quite rapidly. And also it meant that the company could then hire more people and grow at a faster rate, because they were quite hampered before, because there's only so much change you can make on one code base with one set of developers without causing mayhem.
All right, it looks like we have one last question for you, Matt. Do you have any advice for how cross-functional teams can balance autonomy over their evolutionary architecture with consistency across the wider department or company?
Yeah, that's a good question. That's a really good one. So what I've seen work well with a couple of different clients, and what I've kind of recommended before, is almost kind of working at sort of three levels. So you have, if you your overarching objective from a business perspective, and then the business objective kind of boils down to, so like we want to do something, we want to build something, and then okay, well how do we build it? So there should be some cross-cutting principles across different teams that we can agree upon. So for example, we might say, actually, you know what, for this organization, we're all going to use the same cloud provider. So we're going to be buying into making a bet that this is going to be the cloud provider of the future, and we want to use that. We might also say, actually, we're going to unify on the fact that we want everything to be event-driven. We're going to have contract tests in place between services, and so you set in some principles that each team then kind of buys into. And what that means is that each team has the flexibility to kind of define how they build and maintain their part of that, but there's still some kind of governance above that which says that you have to be doing these kind of, or you have to adhere to these principles. And so what I've generally seen work quite well is that at the start of a sort of a large scale project like that, you draw up these principles for what the architecture should look like. at a super high level. So whether it be things like, we're going to implement microservices, we're going to have contract tests between each team, we're going to host it on XYZ cloud provider. And so you have these principles in place, and then the underlying teams, if you like, are then kind of free to have autonomy of how they build their piece, knowing that they'll all fit together under the same principles. And then what's key about that as well is once you've defined those principles, you can codify them as fitness functions and have them running against the system, so that we can be sure that we're not kind of veering off course. So I think it's kind of overarching governance, if you like, across the tech product.
All right, thank you. It looks like that's all the questions we have. Thank you for answering them.
No problem.
And
what I will say, I mean, if you do have other questions that sort of come to you today, tomorrow, later on, do feel free to ping me on my email there, matthew.belcher@codurance.com, and also on LinkedIn too.
Thank you so much. We will see you in the Slack channel just momentarily. Thank you for your time today and your great presentation, Matt.